In this question, we are given the half-life of a radioactive substance is 38 years, and we want to find out how long does it takes for the radioactive substance to decay to 90% of the original amount. In other words, this is equivalent to saying how long does it takes if the radioactive substance remains only 10%. So let's see how to find this one. I'm going to write down this decay model, that is A equals A naught e raised to the power of negative kT. This A represents the final amount of the radioactive substance. This A naught is the initial amount of the radioactive substance. K is the decay rate or decay constant. And T is the time in years or hours. So let's see how to solve this decay model. First, I'm going to use this information, that is half-life is 38 years. And this means we can say that the after 38 years, that is when t equals 38, the amount or the final amount of the decay substance is 50%. So you can say that A equals 50% of the original amount, that is A naught. We can represent this as fraction because 50% is 50 by 100. We write down like this, A naught, or this is equal to half of A naught. So at t equal to 38, after 38 years, the amount of substance remains is half of A naught. We use this equation, that is A equals half of A naught as well as t equals 38. We plug this into the decay model. So let's do that. This means I'm going to plug in A equal to half of A naught. Let me write the model over here. So we have the model A equals A naught e raised to the power of negative kT. Now in place of e, we have to replace this as a half of a naught. So this becomes half of a naught, and this equals a naught e raised to the power of negative k, and we have to replace t also by 38. So this becomes 38. Now we have to solve for k from this equation. We divide both sides by a naught, and when we do that, this a naught will get cancelled. So therefore this equation simplifies to half equals e raised to the power of negative 38k. Now we apply natural logarithm to both sides to determine the value of k. So I apply natural logarithm. So this becomes natural logarithm of half, and this equals natural logarithm of e raised to the power of negative 38k. Now we know that using the power properties of logarithm, this negative 38 comes in front. So therefore we can rewrite this equation as natural logarithm of half. This equals negative 38k times of natural logarithm of e. Recall that the value of natural logarithm of e, this equals 1. So we can simply say that the natural logarithm of e equal to 1, which means I can just remove this, and we are just having negative 38k on the right side. We now solve for k from this equation by dividing both sides by negative 38. So therefore we can solve for k. This equals natural logarithm of half divided by negative 38. We put this into the calculator, and when we do that, we get the approximate value of k. This equals 0.01824. So in the first step, we determine the value of k, and this means we can write down the decay model as by substituting into this equation. So which I'm going to do that. So therefore, the decay model becomes A equals A naught e raised to the power of negative k, that is negative of 0.01824 times t. Now let's go back to the original question. We want to determine how long does it take for the radioactive substance to remain only 10%. So this is equal, and mathematically we can rewrite this as A equals 10% of A naught. Or other words, we can write down this as A equals 10% is 1 over 10th of A naught. So we will utilize this condition plug it into the decay model and determine the time. Let's do that now. So I can write down this A equals half of A naught. Sorry, this is 1/10 of A naught. So in this case, we have to determine the time. So let's replace A equals half 1/10 of A naught into this model. So this becomes 1/10 of A naught. This equals A naught times of e raised to the power of negative of 0.01824 times t. Now we can cancel this A naught. If we divide both sides by A naught, so this A naught will get cancelled, and this becomes 1/10 equals e raised to the power of negative of 0.01824 times t. Once again, we apply natural logarithm to both sides to determine the value of time. So therefore, this equation becomes natural logarithm of 1/10. This equals natural logarithm of e raised to the power of negative of 0.01824 times t. So once again, we apply the power properties of logarithm. So therefore, this complete part comes in front, and we are going to be left with natural logarithm of 1/10. This equals negative of 0.01824 times t times of natural logarithm of e. Natural logarithm of e, we know that it is 1, so this becomes 1. So this it's an equation which we can solve for t. So therefore, we say that the equation for t equals natural logarithm of 1/10 divided by this quantity, that is negative of 0.01824. So let me write down here. So this becomes negative of 0.01824. We plug this into the calculator, and when we do that, we approximately get the value of t as 126.24 years. So it will take about 126.24 years for the radioactive substance to dissipate to 90%, or it will have only 10% of the original amount of the radioactive substance.